So now we're going to look at ionic equations, learn how to analyze the components, break them up so that we can focus on the specific chemistry that's occurring in those equations. So let's go ahead and take a look at what they describe. They describe the ions that are present in solution, what ions are involved in the chemical reaction. So let's say I have a beaker of silver nitrate. I take some water and I dissolve silver nitrate into that beaker of water. Here's what happens. It's a nitrate. All nitrates are soluble. So immediately the silver nitrate dissolves into silver ions and nitrate ions. So that's actually what's in the beaker. I'm going to do exactly the same thing with potassium iodide. I'm going to take some potassium iodide, it's a crystal, and I'm going to, just like silver nitrate was, I'm going to put it in some water. This is water. And as soon as I put the potassium iodide into water, this is an alkali metal salt. It completely dissociates into potassium ion and iodide ion. So that's what I have. I have two discrete beakers, two separate beakers, and now I'm going to mix them. I'm going to simply combine the solution of potassium iodide with the solution of silver nitrate. Here's what's going to happen. The silver nitrate, once I combine it with the potassium iodide, is reaching out in this metathesis reaction for the iodide reaction. These two species love each other. They are going to be tightly bound together into a solid. So now I have one beaker that has silver iodide, which falls out of solution as a solid. The way I represent that in my equation is I simply bring it down as a solid. And I'll go ahead and I'll put solid down here. Now, the thing to remember is that you also had potassium ion and nitrate ion in that solution. So in that beaker with the silver iodide sitting at the bottom, eventually, it takes a little while for gravity to let it settle, I'm also going to have potassium ion floating around and nitrate ion floating around. These are dissolved ions, completely dissociated from each other, and so those guys are dissociated ions in the same solution with the silver iodide, but the silver iodide sitting on the bottom, and these guys are distributed throughout the liquid in the solution, and both of these guys are eyeballing the chemistry. And so they're free ions, they are watching the chemistry, they're in a sense spectators, so we call these spectator ions. All right, and I'm going to show you how to recognize spectator ions. So we call this level of equation right here, and I'm going to go ahead and get rid of all of this writing that I have on here so you can see the chemistry. What we have here is called the complete Ionic equation, and that is this entire equation. You have dissociated ions, and then you have your driving force, which is a solid. These are all in aqueous solution, so I could put aqueous, 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 aqueous. These are no longer dissolved ions. They are in the driving force, a precipitate. That's another thing we could call this, a precipitate, and it is the driving force for this particular metathesis reactions. Here are your spectator ions that are just hanging out. But in total, this entire dissociated ion equation is called the complete ionic equation. And we're going to learn how to do that. So here's the complete ionic equation. What we want to do is I want to identify what we call the spectator ions. Here's how you identify the spectator ions. Look for the ions that are the same on both sides of the equations. So I'm just going to call these SIs for spectator ions. Sorry to the SIs. These are spectator ions. How to identify them? Well, they're ions on the reactant side, and they're still ions on the product side. What that means is they didn't do any chemistry. They just are hanging out there, not doing chemistry, essentially watching the chemistry that actually does go on. So the spectator ions are present on both sides of the complete ionic equation. They're not involved in the actual reaction that's taking place. They are doing nothing at this point. Okay? So once you've identified the spectator ions, you throw them out. It doesn't mean that they're not there, but in terms of the way that you're analyzing the equation, you throw them out because they're not doing chemistry, and the reaction that's left over after you get rid of the spectator ions, that's called the net ionic equation. There it is, coming at you. Okay? This is the net ionic equation. That's really the only chemistry that occurred. Okay? Silver ion combined with iodide ion to become the solid precipitate silver iodide, which is the driving force for the reaction. Summary. Complete ionic equation, that's all the dissociated ions on both sides of the equation. Don't worry about the driving force. You don't dissociate that. And then the net ionic equation, this is what remains after you've identified the spectator ions. And the spectator ions are the ions that are ions on both sides of the equation. I'm going to give you a clue right now. If you've got an alkali metal cation, you can guarantee 100% it's a spectator ion. Why? Because it's always associated with strong electrolytes. And in solution, strong electrolytes are always dissociated. And if it's always dissociated, then it has to be a spectator ion. It's not doing chemistry. I can say the same thing for nitrates, because if you remember your solubility guidelines, nitrates in ionic compounds are always soluble. Acetates are a different thing. I'll show you why. But nitrates and alkali metal cations will always be spectator ion. Procedure for determining the net ionic equation. Determine if each substance is soluble. Determine whether the soluble substances are strong electrolytes, weak electrolytes, or non-electrolytes. Dissociate only soluble, strong electrolytes. Got to know your solubility rules. Omit the spectator ions from the reaction. So let's do some practice. The first thing you have to do in these problems is you have to come up with a balanced equation. So in this case, it's a metathesis reaction. So sodium is going to get together with nitrate. Barium is going to get together with sulfate. So we're going to flip those around. We're going to swap partners, and here's what we come up with. Now I've gone ahead and I've balanced the equation, so we don't have to worry about that. Step 1, dissociate the soluble, strong electrolytes. Don't dissociate anything else. You need to know your solubility rules for this. All right, so this is an alkali metal salt. It's also a sulfate, but the easiest thing to do is look at sodium. It's an alkali metal salt, so you're going to have 2Na plus aqueous. If you don't have the charge on it, the correct charge on it, you are wrong. If you don't have the aqueous, technically, you're wrong. This is sulfate. It's a 2- ion. It's an aqueous solution. That's aqueous. And then we have barium nitrate. It's a soluble salt because all nitrates are soluble. So there's barium 2+ ion, aqueous. And then you have 2 nitrate ions, 2NO3- aqueous. Barium sulfate is not a soluble, strong electrolyte. Now, how do you determine that? You look at sulfates on the top half of your solubility rules, and you see that most sulfates are soluble, strong electrolytes, but there are exceptions, and barium is one of those exceptions. So you just put this down here as barium sulfate solid. And then finally, we've got sodium nitrate. It's an alkali metal salt. It's also a nitrate, so we know it's soluble. That's 2Na+ aqueous. And I'm going to squeeze this into nitrates, aqueous. Okay, this is the complete ionic equation. Okay, this is the complete ionic equation right here. All the ions that can be dissociated are dissociated. Next thing we want to do is we want to find the spectator ions. That's easy. We've got sodium cation, which is a free ion on the reactant side. Sodium cation is a free ion on the product side. Nitrate is a free ion on the reactant side, and nitrate is a free ion on the product side. These are your spec ions. Throw them out. Once you've identified them, throw them out, and that's going to leave us with barium 2+ aqueous plus sulfate 2- aqueous, and that's going to make barium sulfate. It's a solid. All right, and this is your net ionic equation. And that's usually the goal. Now we know what the chemistry that's going on in this ionic equation actually is. All right, let's go ahead and let's take a look at the next reaction. We've got barium chloride plus silver nitrate. This is a metathesis reaction, so we're going to swap partners. Barium's going to get together with nitrate, silver's going to get together with chloride, and that's going to give us this. The reaction is already balanced. By the way, we just call this the molecular equation or just the equation. All right, so we dissociate the soluble strong electrolytes. All chlorides are soluble except for silver, lead, and mercury, so this is a soluble salt. And so that's going to give us barium 2+ aqueous. We're going to have 2 chloride ions, aqueous, plus 2 silver ions, aqueous, plus 2 nitrate ions, aqueous. What's the solubility rule for silver nitrate being a soluble, strong electrolyte? It's a nitrate, and all nitrates are soluble. This is barium nitrate. It's a soluble salt for the very same reason. So we'll go ahead and we'll dissociate it. That'll be barium 2+ aqueous plus 2 nitrates, aqueous. And then we have silver chloride. Now, all chlorides are soluble except for silver, lead, and mercury. So this is our driving force, guys. This is the compound that's not soluble, so we just bring it down as 2AgCl solid. This is our driving force, and it's a precipitate. Okay? This is the complete ionic equation. All compounds that can be dissociated are dissociated into their ions. Let's find the spectators. We've got barium ion on the reactant side, and barium ion is a free ion on the product side. So in this case, barium is a spec ion. And then we have nitrate. Nitrate is always a spectator. You can count on that one. So nitrate is a spec ion. So we're going to throw out the spectator ions. That's going to give us 2 silver plus 1 aqueous plus 2 chloride ions, aqueous, and that's going to give us 2 silver chlorides, solid. Now, while this is the net ionic equation, anytime you can reduce those coefficients to simpler numbers, you do. All I have to do is divide all of these by 2, and that gives me Ag plus aqueous plus chloride ion, aqueous, making silver chloride solid, which is a precipitate. It's the driving force. It's a precipitate. I'll just say precip. And so this is the net ionic equation. This equation right here is our net ionic equation. And by the way, I have got, if you missed or just are too tired to write it out, although I would have you write, I would suggest that you write out all of these equations. Here are the solutions for you. You don't have to do them yourself if you don't want to, but you should. Okay? Let's do a couple more examples. All right, so here is sodium acetate, and this is nitric acid. It's a strong acid. We're going to swap partners, so the H is going to go with the acetate and the sodium is going to go with the nitrate, but you can find the spectator ions over here. Alkali metal, cation, nitrate, always spectators. So here we go. And this is our driving force. So here's the molecular equation. We're going to go ahead and dissociate all the soluble strong electrolytes. We'll do it a little bit more quickly because hopefully you're getting tuned into this and you're making some predictions. So this is sodium cation, aqueous. It's a soluble strong electrolyte. The rule is this is acetate. All acetates are soluble. O2 minus, aqueous. This is a strong acid. Strong acids are strong electrolytes. So we'll dissociate that into H plus, aqueous, plus nitrate, aqueous. Then we've got acetic acid. This is a weak acid, and weak acids are weak electrolytes. That is why this is your driving force. And I told you I was going to show you a situation where acetate could be a driving force because your solubility rules say all acetates are soluble. Well, that is for ionic compounds. This is acetic acid. It's not an ionic compound. It's a molecular compound. So those rules don't apply to it. And so we just drag this down as HC2H3O2. It's not a solid. It's not a gas, not a precipitate, not a non-electrolyte. It's a weak electrolyte, and it is dissolved. So it is still aqueous. However, it's a dissolved molecule, and it has removed 2 ions from solution, which is what driving forces do, and I'll show you that in a second. And then we have Na plus, aqueous, and I'm going to squeeze in the nitrate, aqueous. Okay, here's your complete ionic equation. I'm going to find the spectators. Well, the sodium cation is an alkali metal cation. You know it's a spectator ion. All nitrates are soluble in ionic compounds, and so it's going to be a spectator ion always. All right, so here is our net ionic equation after we've thrown out the spectators. I've got H plus from the strong acid, and I've got acetate from the sodium acetate, C2H3O2 with a -1 charge, aqueous, and here's our driving force, the weak acid, HC2H3O2, and it is also aqueous. It's dissolved, it's just not completely dissociated. It's only partially ionized. All right, so how is this the driving force? We have to remember what driving forces do. Driving forces remove ions from solution. What two ions got removed from solution? H plus and acetate. They got removed from solution. They combined to form the driving force, acetic acid, our weak acid, our driving force. Okay, and this is our net ionic equation. All right, let's try a couple other things. One more, zinc sulfide plus a strong acid, hydrochloric acid. This is zinc chloride and hydrogen sulfide gas. Nasty smelling stuff. All right, so here's your molecular equation. We're going to dissociate all your soluble strong electrolytes. Now take a look at sulfides, which are on the bottom half of the solubility guidelines. And you see most sulfides are not soluble. There are exceptions, but zinc is not one of those exceptions. So we're simply going to pull this down as zinc sulfide. And it is a solid. It hasn't changed from that. It hasn't dissociated. On the other hand, this is a strong acid, and strong acids are strong electrolytes, so it's going to completely ionize into two of these H pluses plus two chloride ions, aqueous. And then we have zinc chloride. Well, all chlorides are soluble. That's in the top half of your solubility guidelines. Except for silver, lead, and mercury, zinc is not one of those, so it will dissociate. So that'll be zinc 2 plus aqueous plus 2 chloride ions, aqueous. And then finally, let's take a look at this guy. Well, you may not know that this is actually wants to be a gas, but even as a molecular compound, at best, it's a weak electrolyte, a weak acid and a weak electrolyte. We call it, once it's dissolved in water, it will, to a tiny, tiny bit, ionize, and whenever it does, we call it hydrosulfuric acid. I know that's a weird one, kind of breaks a few rules, but that's okay. But it is our driving force. So we bring it down as an intact molecular compound. Whether you consider it as a gas or just a weak acid, it is definitely our driving force in this reaction. All right, so here's our complete ionic equation. Let's go ahead and find our spectator ions. Well, I'm not seeing any ions here. H plus, I don't see H plus over here. Hydrogen is bound up in the driving force. But I do see the chloride ion as a free ion on both sides of this reaction. So in this reaction, we only have one spectator ion. And so we're going to toss it out, and that's going to give us zinc sulfide solid plus 2 H pluses aqueous, and then we're going to have zinc ion floating around over there, but it participated in the chemistry, and that's aqueous. And then finally, our driving force, H2S. And I'll go ahead and list that as a gas because that's actually what it would like to be. It's a nasty, smelly, toxic gas. You really don't want to smell this. It smells like rotten eggs or other unsavory smells. And this is our net ionic equation. Okay? Hopefully that's enough practice for you. You should try these on your own. If you did not write all of this down, you didn't follow along, you can find all the solutions right here. They're more legible than in the version that I just did for you. Don't forget to put the phases in. And we'll end the video with this clicker question. All right. So when potassium hydroxide and nitric acid are mixed, a metathesis reaction occurs. What are the spectator ions in this reaction? Well, you might already know, but we're going to go ahead and we're going to work the whole problem. Now, you should recognize potassium hydroxide as a strong base. And if it's a strong base, guys, it's a strong electrolyte. And if it's a strong electrolyte, it dissociates completely in water. Okay? So this guy's going to dissociate completely. Hopefully you recognize this. It's a strong acid. And if you recognize it as a strong acid, you must know that it dissociates completely and is a strong electrolyte. Okay, so let's go ahead and let's do this entire reaction. So I've got KOH plus HNO3, nitric acid, and this is going to be a metathesis. The hydroxide is going to get together with the hydrogen ion, form our driving force, which is the non-electrolyte. This is a non-electrolyte, okay? It's water. All right, and then the potassium ion is going to get together with the nitrate, and that's going to give us KNO3, potassium nitrate. Okay, here's your molecular equation. So once I mix these, or actually, let's just start this way. This is a crystal, potassium hydroxide. I put it in water. It dissociates. It dissociates into potassium ion, aqueous, and hydroxide ion. And it's virtually a complete dissociation. This is nitric acid, a strong acid. It does exactly the same thing. It dissociates into H+, aqueous, and nitrate ion, aqueous. All right, this is our driving force. It's a pure liquid. And so when we put this down, we don't dissociate this. This is H2O. It is a pure liquid. It is our driving force. It is a non-electrolyte, a molecular compound that does not dissociate. On the other hand, potassium ion and nitrate are just hanging out, watching the chemistry, spectating, and their ions. So nitrate, which is always a spectator, alkali metal cation like potassium is always a spectator. So we can answer the question right now. The answer is C. Potassium and nitrate are our spectator ions. However, let's go a little further because I want to show you something. All right? What's left is the net ionic equation for this strong base, strong acid reaction. It's called this is a neutralization reaction. And neutralization is just another word for an acid-base neutralization reaction, and it is the other type of metathesis reaction that we talked about. So that's going to give me a net ionic equation of H plus aqueous plus OH minus aqueous makes our driving force water. All right, so here's our net ionic equation, and I'm going to give you a gift, okay? And that gift is, when you have a strong acid, strong base reaction, you have two products. You have a salt and water, and the net ionic equation is this. Pick any strong acid, any strong base. This is the net ionic reaction. And in acid-base chemistry in general, this is what we're looking at as being really the crux of the matter. But particularly if I give you a strong acid like nitric, like HCl, like HBr, like HClO3, HClO4, any of those strong acids with any of the strong bases that I've given you, lithium hydroxide, sodium, potassium, rubidium hydroxide, calcium hydroxide, this is the chemistry. This is what's happening. These two guys, hydrogen ion, hydroxide ion, are getting together to make this. And that makes your life easier if you understand that. Okay, that's enough for that video.